Okay, today we're diving into one of the most frankly mind-bending ideas in all of physics. We're not just talking about studying black holes, we're talking about hacking them to steal their energy.
I know, it sounds like something straight out of science fiction, right? But believe it or not, for the last 50 years, some of the smartest physicists on the planet have been crunching the numbers on this exact question. And the answer they came up with is a resounding yes, leading to a concept with a name you are just not going to forget: the black hole bomb. So to even begin to understand how this works, we need to take a trip to a really, really weird place called the Ergosphere. Now, this isn't inside the black hole, it's a region of space just outside the event horizon, where the black hole's spin is so powerful that it literally drags the fabric of space-time along with it. In here, you can't stand still. You just can't. You're forced to get swept along for the ride.
And it was this bizarre swirling region of space-time that got the great Sir Roger Penrose thinking way back in 1969. He came up with this brilliant thought experiment for how you could tap into that incredible rotational energy. We now call it the Penrose Process.
Okay, so how does it work? Well, imagine you drop something into the ergosphere and you time it just perfectly so that it breaks in two. One piece is designed to fall into the black hole. But, and this is the crazy part, because of the physics in there, it falls in with what we measure as negative energy. So to keep the books balanced, conservation of energy, the other piece gets shot out with more energy than the original object even started with. You've essentially just stolen a tiny bit of the black hole's spin. If that's a little hard to wrap your head around, think of it like this. Imagine you throw a big piece of sticky clay at a spinning carousel. A chunk of it breaks off and flies away. That chunk can actually get flung away faster than the speed you threw the original piece. Where'd that extra energy come from? It came from the carousel's spin, slowing it down just a tiny bit. The Penrose process is just the cosmic, supercharged version of that. And get this, we're not talking about a small effect here. The math shows that with a black hole spinning at its maximum possible speed, you could get up to a 20.7% energy gain. That is a staggering amount of free energy pulled right out of spinning spacetime. But as incredible as the Penrose process is, it turns out there's a version of this that uses waves instead of particles. And it's even more powerful. It's called superradiant scattering.
So what is superradiance? Basically, it's what happens when you shoot a wave, say a light wave, at a spinning black hole. Instead of just getting absorbed or bouncing off like normal, the wave can actually come back amplified. It bounces back with more energy than it went in with, and once again, it steals that energy right from the black hole's rotation. Now, for this cosmic amplifier to kick in, there's just one simple rule. The frequency of the wave you send in has to be lower than the speed at which the black hole is spinning. If you meet that condition, boom, you get amplification. If not, the wave just gets swallowed up, like you'd expect. Okay, this is where things get truly explosive. A few years later, in 1972, two physicists named William Press and Salt Tucholsky took this whole idea of superradiance a step further. They asked a simple question: what happens if you don't let that amplified wave escape? And their idea became the black hole bomb. Imagine you could build a giant perfect mirror completely surrounding a spinning black hole. Now a wave goes in, hits the black hole, and gets amplified. It shoots out, hits the mirror, and gets reflected right back in, to be amplified again, and again, and again. You create this runaway feedback loop where the wave's energy just grows and grows exponentially. And what's so cool is they weren't just thinking about a weapon. You can see it right here in their original paper. They immediately saw the practical use. They said you could just open a little window in the mirror, let some of that energy out in a controlled way, and you'd have created the most incredible power source imaginable. For 50 years, this whole idea was one of the wildest theories out there. I mean, how could you ever test something that needs a spinning black hole and a mirror the size of a solar system? Well, it turns out the solution was proposed almost as soon as the theory itself was. What's just amazing is how fast all this happened. Penrose published in '69. Just 2 years later, a Soviet physicist named Yakov Zeldovich suggested a way to test the basic idea of superradiance. Right here on Earth, no black hole required. A year after that, we get the bomb theory. It was a whirlwind. Zeldovich's idea was pure genius. He realized you could build an analogy. You don't need the ergosphere. You can use a spinning, absorbing cylinder, something made of metal. And you don't need light waves trapped by a giant mirror. You can use twisted electromagnetic waves or even sound waves. He argued that the fundamental physics would be identical. But There was a catch. A massive, massive catch. To make his experiment work with light waves, Zeldovich calculated the cylinder would have to spin at least 1 billion times per second. That was completely impossible then, and it's still completely impossible now. So the idea, as brilliant as it was, just sat on a shelf for decades.
So how in the world did we go from an impossible number to an actual lab experiment that worked? Well, this is the story of how a 50-year-old problem was finally cracked, not by brute force, but with an incredibly clever workaround.
See, the problem was never the theory. It was just that insane rotational speed. So scientists realized maybe we don't need to spin something that fast. Maybe we can use a different kind of wave and a much smarter way of trapping it. And this is the brilliant setup they came up with. Instead of light, they used low-frequency electromagnetic waves from a special circuit. And here's the key. The coils of the circuit itself acted as the mirror, trapping and reflecting the waves back onto a simple, rotating aluminum cylinder. This design meant they could finally see the effect at speeds that were actually achievable in a lab.
So what was the smoking gun? The proof? It was something called negative resistance. Now think about it. Normally, a spinning metal cylinder would absorb energy from the circuit. That's just normal resistance. But once they spun it fast enough, past that critical frequency, it started doing the exact opposite. It started adding energy back into the circuit. It showed negative resistance. That was the undeniable proof that energy was being pulled from its rotation. The amplification was real.
And what's so wild is that this exotic black hole physics had been kind of hiding in plain sight all along. The experiment showed a direct link between this Zeldovich effect and a common induction generator, which, also generates electricity from rotational motion.
So let's just recap this incredible journey. We now have lab proof that yes, you can actually steal energy from a spinning object. Superradiance isn't just a cool idea, it's a real cosmic amplifier. That means the black hole bomb isn't just a thought experiment, it's a real physical instability. A 50-year-old theory, born from the edge of a black hole, has finally been proven right here on Earth. And that leaves you with one last, really exciting thought. Proving this idea was once thought to be impossible. It really makes you wonder, what other profound secrets about how the universe works are just sitting there, buried in old theories, waiting for the right clever experiment to finally bring them into the light?